So we're going to get started, and I'm just going to go over, so review a little bit from 2.1, get into 2.2, maybe we'll get into 2.3, we'll have to see. But what we talked about last time was this topic of relations. And so relations is we took some inputs that we could freely choose, and referred to this as being independent choice, or the symbol for this choice we would call an independent variable x. So we would choose, say, the number 5. And say the number 3 and the number 10. And then we put these into our relation. We can symbolize this with the letter R. And then we got some outputs. Now, why the outputs are the way they are, who knows? This could be chosen by someone, like if I walk up to someone and say, I'm going to tell you the number 5. What's the first number that comes to your mind other than the number 5? What would be the number that comes after that in your mind? Not necessarily in order. And they say, when you tell me the number 5, for some reason I think of the number 10. You say, okay, so the output is 10. Go up to another person, say, give me another number, or the first number that pops into your mind when I say the number 3. And if number 3 shows up in your mind, pick a different number. What would be the second number, perhaps, that pops into your mind? And they say 4. Ask another person the same question about the number 10. Say the second number that pops into your mind when I say the number 10. And they say 100. So what's going on? We choose these numbers, and then we get some outputs. These depend upon the inputs. The inputs we got to choose freely, and we say these are independent. And these outputs, we just got to depend on whatever we put in as inputs. So we say these are dependent. Now, that being the case, we represent these inputs and outputs in 3 different ways. And again, I'm just reviewing from last time. So I'm just going to write these down so I don't forget what they are. So one way of remembering these is what I call a domain and range graph. Now the domain contains all of our inputs, and we usually write these in order. So go 5, 3, 5, and then 10, instead of 5, 3, and 10. And in the range are all the outputs. And we can list these in order as well, for 10 and 100. And in our example, if we input a 3, we got a 4. We input a 5, we got a 10. We input a 10, and we got a 100. So we can represent the inputs and outputs like that. The other way we could do this is with ordered pairs. So you have an input, comma, and then an output. So for the inputs, and those will always be first. And then we have 10 for the output, 4 for the output, and a 100 for the output. And the key thing here is no matter what, inputs are going to be first, outputs are going to be last. Finally, the last thing we're going to do is graph these on a Cartesian plane. And I'll get into the details of how the Cartesian plane works a little later. Now for size, because this is such a small board, I'm going to not do this to scale. So you have 4, 10, and 100, and 100 seems kind of close to 10, but so we don't have to write 100 way at the top, beyond somewhere the ceiling. Excuse me, I'm just going to put it right there. Now this axis will be our outputs. And this axis, the horizontal axis, that's for our inputs. So what we can do, where we have 3 and 4 intersect, we'll place a point. So there's a vertical line at 3 and a horizontal line at 4. That gives us the input of 3, the output of 4. We put a point where the lines that pass through 3 and pass through 4 intersect. Next, we have a vertical line for the input 5. And again, horizontal line for the output 10. Where they cross, we'll put a point. And then for the input 10 and the output 100, where they cross, we'll put a point. So this is how we can graph our relation. And that's where we left off from last time. Now, any questions about this so far? And just let me say, welcome. I see you're here, and I hope you had a wonderful weekend. And we're just going to sort of pick up where we left off. Again, we're going to be looking at the rest of 2.1. We'll get into 2.2, maybe some of 2.3. We'll have to see. And I'm going to take a look at the homeworks and make sure the due dates are adjusted so they're reasonable. Now, the relation that I just described was pretty random. I chose an input, say 3, and for some reason I got a 4. I chose an input 5, and for some reason I got a 10. There wasn't much rhyme or reason behind why the outputs were being paired up with certain inputs. Seemed pretty random. For us in this class, this is usually not the case. For this course, we're not going to have random outputs. We're going to be dealing with outputs that result from some kind of a formula. In other words, we're going to take whatever input we get, and we'll do the same thing to that input that we would do to some other input. Let me give you an example. So we might do something like this. And if I'm going too fast, let me know. So let's say we're going to do this kind of a formula. The output will be twice the input plus 1. So what that means, my input and my output. Well, let's pick some inputs and generate some outputs. So let's start kind of easy. Let's go with an input of 0. So if I input 0, which I freely choose, well then what's my output going to be? Well, my output clearly depends on my input. My input influences the output, whether the output likes it or not. So that means even though I independently choose my inputs will be dependent upon my choice of input. So I'll go 0 times 2 plus 1. And following your order of operations, multiplication is done first, addition is done second. I have an output of 1. If I choose 1, 1 times 2 plus 1. Well, this is 2 plus 1 will be 3. And then let's choose 7. Lucky number 7. Well, we'll get 7 times 2 plus 1. 7 times 2 is 14. 14 plus 1 is 15. So we've picked 3 outputs, and then we have, we picked 3 inputs, now we have 3 outputs. So I'm going to summarize this a little more succinctly. As a domain and range graph, we got something like this. D for domain and R for range. Now, as ordered pairs, we would write it like this, where the inputs are first and the outputs are second. 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 7 times 2 plus 1 is 15. Finally, we could graph this. And again, it's not really to scale. I'm going to call this my inputs axis. This is my outputs axis. So when I input 0, think of a vertical line here, 0. Inputs will be vertical lines along the horizontal axis. My output, which is always a horizontal line on this vertical axis, was 1, so I have a point here. Input of 1 and an output of 3. And then an input of 7. And an output of 15. Now we're going to talk about making these graphs more in the next section. So I'm sort of jumping ahead here. We'll get into this more about why vertical lines are being drawn along this inputs axis and why horizontal lines are being drawn up and down the output axis. But this is, when we do get to graphing this, this is what it would look like. Any questions about that? Let me switch on my chat real quick. All right. So we're going to talk about a special kind of relation. And the special kind of relation is called a function. Now, a function is a type of relation. Now, where functions come from, they actually come, to a certain degree, they probably come from physics. Excuse me, and it has to do with the idea of time. And you could think of it like this. Each output has a unique input. So each output has a unique input. You can think of it like this. If you imagine the input as time, and the output is location. So what would happen if you had two locations with the same input? In other words, the inputs weren't unique. Well, what that would essentially mean, let me give you an example of why we want functions so much. If input is time and output is location, let's say we have an ordered pair. And since input is time, let's say this is 4 p.m. And where's your location going to be? Say it's Taco Bell. So here's our input, and here's our output. We have some sort of function or relation, I should say, where you give it time, it kicks out a location. You input time, you output a location. So 4 p.m. is Taco Bell. I just finished my homework. I'm going to get an early dinner. And then let's say it's 6 p.m. Again, that's my input. My output will say I'm at home. So here we have a situation where input is time and output is some kind of location. Now, according to the definition of a function, every output has a unique input. In other words, there are no duplicate inputs. Now, why would we be interested in that? Well, let's take an output. And let's say this is the mall. Now, so far, these outputs, there are no repeated inputs. But let's repeat an input. Let's see what happens. The world's about to go crazy. Now, let's assume, and I believe the Roswell Mall has no Taco Bell in it. So at 6 p.m., I'm also at the mall. And let's say I don't live at the mall. So let's maybe go back here. I was talking about Taco Bell. So let's go 4 p.m. again. Now, Roswell Mall does not have a Taco Bell. So if you look at my data, What's wrong with this? Well, at 4 p.m., I'm supposedly at Taco Bell, and there's one down on Main Street, closer to NIMI. But also at 4 p.m. I'm at the mall. So the problem here, if I have duplicate inputs, this says I'm at two places at the same time. So we define functions as ordered pairs or domain and range plots or a set of inputs with their outputs where we don't get duplicated inputs. And the reason we probably don't want duplicated inputs, excuse me, a lot of functions come out of this study of science called physics, or science called physics. And with physics, you deal with time. And when you're dealing with time, you can't be at two different places at the same time. So it's very important. So when you think about what is a function, think of it as sort of time as an input and location as an output. And we don't want the same times for different locations. That means we're breaking some rule of the cosmos. Now you could argue if you could warp space and time and you could bend space so the Taco Bell is next to the mall, then you could technically pull that off. We're not talking about that. So the key thing with functions no duplicate inputs. No duplicate inputs. Now, what about duplicate outputs? Well, that's perfectly fine. That's perfectly okay. This doesn't break our understanding of the cosmos if we think as input as time and output as location. And I'll give you an example, because we actually live this every day of our lives. So again, input is time, output is location. So input is time and output is location. So 8 a.m. Say you're at home. 12 p.m. It's time for lunch. Maybe go to the Taco Bell. And then finally, 8 p.m., you're at home again. Now, this is still a function. We have an 8 a.m., 12 p.m., 8 p.m. These are three different times. In fact, to make things a little even clearer, it's called 7 p.m. So you have three different times. But we're home, we're at lunch, and we're home again. This is normal. This is fair. This is how our universe works. So at times, we can be at the same place. I'll be home at 8 a.m. I'll be home at 7 p.m. That makes sense with the cosmos. And again, physics is a study of the cosmos. And a lot of these ideas of functions and relationships between different types of variables, independent, freely chosen variable, and there's a dependent variable that's a modification of the input, the independent variable. These come from the field of physics. So it's perfectly fine to be home at two different times. That's okay. So you can have duplicate outputs. So any questions about that? Now let me do an example. Is this function? Well, let's say it maps like this. So what we have, if we input a 1, we output a 7. If we input a 2, we output a 7. If we input a 3, we output an 8. Now, is this a function? Well, if we look at our inputs or our domain, they're all unique. And they only match to one output. To make this a little clearer, though, if we create the ordered pairs for all these matchings, there's a unique input for each ordered pair. So every output has a unique input. So this first 7 gets a 1. The second 7 gets a 2. The first and the second 7, they have different inputs. That's fine. That's what we want. And this 8, it has an input of 3, which is not 2 and not 1. So all the inputs are different. Because all the inputs are different, this is a function. Now let's say I change things a bit. In fact, do it this way. Let me put another number in here. It's going to be out of order. So let's do this in terms of coordinates. This one's kind of a mess. So 1 goes to 4. 1 also goes to 5. Now 2 goes to 6. And 3 also goes to 6. So figuring these things out, it can help to put things in ordered pairs. But there's another thing to watch out for, and I'll show you in just a bit. So if we look at these right here, the output has a 1, this output has a 2, this output has a 3. So far, the inputs, they're all different, till we look at this one. These two inputs are the same. And you can see this in your domain range graph. Give the R here for range. Because the 1, this input gives you 2 different outputs. So because the inputs are going to be duplicated, or another way of putting it, because this input can go to 2 different places, this is not a function. There's another way of thinking about this. Let's say we're talking about money. And let's see, it used to be in restaurants, I don't know if this is the case here still, but it used to be that if you were serving in restaurants, you wouldn't necessarily get a minimum wage. You would get a smaller wage, and then you would make tips on top of that. So let's say you put on an hour of work, and you get $4 per hour. Or is it $5 per hour? Which is it? If I put an hour's worth of work, do I get $4 or $5? Which? Because according to this graph, I could get either one. Again, this is another reason why we're interested in functions. Again, this has to do with time, except this is time as an amount, or any amount for that matter. For example, if I was, say, collecting an unusual form of sand that was used in some industrial process, say pounds, like a pound of pure silica, and I could be totally getting this wrong on the pricing of a pound of pure silica. But is that pound going to be $4 or is that pound going to be $5? Well, I want to know which one I'm going to get. So that's why we don't want duplicate inputs. Am I going to get 4 or am I going to get 5? Which is it? So that's why we're very keen on making sure inputs are not duplicated. Now, we need to talk about function notation. So far, I've been presenting inputs and outputs roughly like this. There's an input. There's some kind of a relation. And this is usually a mathematical formula. And there's an output. So for example, we had output, input times 2 plus 1. That was one sort of mathematical process that was behind our relation. Now there's infinitely many formulas you could come up with. Certainly it's not going to just be this one. But we try to make things a little more concise. Typically, we let our input be x. And then our output, I know what you're thinking, but we usually call it f of x, though oftentimes we'll call it y as well. So what happens when we make these changes? So what we'll get, instead of output, we'll have f of x equals, instead of input, we'll have x times 2 plus 1. We'll write it using this notation. Or to make it a little more concise, f of x is 2x plus 1. Again, this here means 2 times x. So we let x represent the input, and we let f of x represent the output. So then what we would do with our example from before, is 0, 1, 7. We have 1, 3, 15. What we formerly called input, what we formerly called output. Now, why do this? Why are we making things seemingly more difficult? Why not just stick with input and output? Well, part of it is in mathematics, we try to be concise with our notation. So instead of having the right input, we'll just write the letter X. Instead of writing the word output, we write f of x. It's just a shorter way of doing things. And there's some symbolic power in it too, and I'll go over it. We can use this notation to help organize our calculations. Any questions about this so far? All right. So we're going to talk about an idea called substitution. What substitution is we replace a variable everywhere with a number. Let me word it a little differently. Underline everywhere. Everywhere, we're going to replace a variable with a number. So when we work with functions, we're going to give ourselves, we're going to choose an input. Say, we're going to choose x to be 3. And then in our formula that's behind our relation or behind our special kind of relation called a function, we're going to do some calculations that come up with an output, f of x. So what we've done, we've taken input into our relation to get an output. We're going to reword this as an x goes into our relation to get an f of x. So this is how we're going to do this. Let x, our input, be 3. So let's go back to our formula, the one we've been using. For our output f of x is 2x plus 1. Now we've chosen x to be 3. We want that to be our input. So that means everywhere we see x, we're going to replace it with 3. So that means this will become a 3. And then this x becomes a 3. Questions so far? This is what we call substitution. So now what we're going to do, we'll do the calculation. So 2 times 3 is 6, plus 1 is 7. And so this is our answer. So the advantage of this new kind of notation is this is where we have our input. F symbolizes we're changing this input. And this here tells us the output. So a better way of describing this is X goes into F, and the output is F of X. And that's how we often think of it. So let me do an example. Let's make this a little more concise. So let's say we're going to find f of 2. Well, what this means is that x is equal to 2, or this is going to be our input. Then our output is going to be f of 2. We replace all the x's with 2, which will be 2 squared, which equals 4. 2 squared means 2 times 2. So that's going to be 4. And this is our output. So we get an ordered pair. Input, output, well, the input was 2. The output was 4. So input 2, the output 4. Or f of 2 is equal to 4. Let me do another example. Let's say we have something like this. And I want to choose some inputs represented by x. And we're going to compute some outputs represented by f of x. So first off, let's choose 1. Input of 1. So for x equals 1, our output is we'll take all these x's, replace them with 1. So f of 1 will be 1 squared plus 2 times 1 plus 1. Or 1 plus 2 plus 1. Writing 1 2 different ways, but they're the same number. I guess I have 2 different ways of imagining 1, but they both mean the same thing. So 1 plus 2 plus 1 is 4. So that means our output is 4. And the input is 1. Let's do another input. Let's say we choose 2. So now I'm going to replace all the x's with 2's. So you have 2 squared plus 2 times 2 plus 1. Now there's a convention that's done in mathematics that when we replace a variable with a number, we oftentimes put it in parentheses. You don't always have to do that. Like I didn't do it last time. But I'm going to replace this x with a 2 in the parentheses. Remember, a number next to a number in parentheses means multiplication. Now you could have done this just as well. that would work just as fine. So I have 2 squared, which is 4. 2 times 2 is 4. And then a plus 1. 4 plus 4 is 8, plus 1 is 9. So for an input of 2, we get an output of 9. Let's do one more. Let's choose an input of 3. So we let x be 3. Replace all the x's with 3. So 3 squared is 9. This is 6 plus 1, or this will be 16. So for an input of 3, we get an output of 16. And that's the idea of function notation. Any questions about that? So we're going to talk about graphs. And again, this is a bit of a review. But we have a horizontal axis, and we call this the x-axis. So that horizontal axis is the x-axis. The vertical axis that crosses at x is 0. It's also a number line. Vertical of 0. And we oftentimes call this the y-axis, or, and since we're using f of x, the f of x axis. So there's a little bit of there's different parts to this thing. This is called the first quadrant, Q1. This is the second quadrant, Q2. Third quadrant, Q3. Fourth quadrant, Q4. And again, this is just sort of a review of what this thing is. Key thing here, this is called the origin, or the point 0, 0. So how do we graph with this thing? Well, what we do is this. It's a -3 there. Now let's say I'm going to graph 2, 3. I'm just going to get another pin here. So this one's just barely making it. So here I have a Cartesian plane. And this is the x-axis. And we'll call this f of x. But it could also be y. So here's our x. And here's our f of x. So again, ordered pairs, input is always first, x. Output is always second, f of x. So to graph this, we look along the inputs x, and we find a 2. So we can put a vertical line on the paper or in our imaginations at x is 2. So that's x is 2. Then for the output, outputs are always horizontal lines. Along the output axis. So this would be f of x equals 3. And where these cross, that is the location of that point. So this would be 2, 3. That's where that point is located. Questions about that? So how does this work for functions? Well, what we typically do is we need to generate some ordered pairs, or some inputs and outputs. So let's say we're going to graph f of x equals x squared. Well, let's pick some inputs. So let's say we have these. In fact, what I'm going to do, I'm going to write this horizontally instead so we can look at the graph without having to erase anything, so we can see it all come together. Do it like this. Well, what this says is that whatever we have for x, we're going to square it. So f of -2, this is -2 squared, or -2 times -2 is 4. So the output will be 4. F of -1, this is -1 squared. -1 times -1, negative times negative is a positive. We'll just get 1. For 0, 0 times 0 is 0. For 1, 1 times 1 is 1. Finally, for 2, 2 times 2 is 4. So now we have our inputs and our matched outputs. So now we're going to graph this thing. So let's think about -2. We're going to graph -2 with an output of 4. So we're going to have a vertical line at -2. And again, I'm going to draw it on the board, but you could draw it in your mind. Input of -2, outputs are always horizontal. And so where these cross, I put a point. For -1, well, I get an output of 1. And where those cross, I get a point. For 0, input of 0, I get an output of 0. Like down here, this would be -1, so you have 1, 0, -1. So output of 0, where those cross. Well, this is just the origin right here. Now for 1, input 1, an output of 1. An input of 2. Output of 4. So finally, to do this graph, I'm going to connect the dots going left to right. So starting at the left, as I move over, the next dot to the right's down here. So I'm going to do that. The next dot to the right is down here, like that. Next dot to the right is up here. And then the next dot to the right is up here. And that's going to be my graph of f of x equals x squared. Now, if you're familiar with this graph, you probably have seen that the real graph looks like this. It's smoother, sort of a loop. And that is true. If we had more inputs in between the inputs that we chose, like -1.5, -0.5, 0.5, 1.5, maybe -3, 1 3/4, 1/4. If we pick more and more inputs and connect all the points, this gets smoother and smoother and smoother. And then we connect these dots. We're going to get that up there. So what I'm going to show you now are what are called, in a sense, canonical shapes. And these are functions that you'll run into later. You can generate them yourself, see what they look like. I'm going to give you roughly what they look like. One. So f of x equals x. It's a line that looks like this. We're going to study this more in a little bit. If we take the absolute value of x, we get something that looks like this. f of x is x squared. F of x is the square root of x and for this one you can only use positive x's for your inputs. You can't use negative numbers for outputs. F of x equals x cubed. We haven't talked about cube roots yet, but we'll get to those. That's the cube root of x. So these are canonical graphs. These are graphs that, as we get more and more into algebra, knowing what a function that's based on x, based on the absolute value of x, based on x squared, based on the square root of x, maybe it's based on x cubed, maybe based on the cube root of x. These give us sort of a starting point for analyzing some of these functions. Questions about that? Let me make sure I might have spelled canonical wrong. I'm not sure. There might be a second in. Someone will have to double check that. Type it into Microsoft Word and see if this gives you a red squiggly line. But any questions? All right. So again, you can take these functions, you can create them on your own. You can generate the inputs and the outputs, choose some inputs, generate your outputs, and you'll get those types of shapes for those types of functions. Last thing I want to mention, a couple things actually. Domain and range. And this is from a graph. So domain, again, it's all the inputs. Or all possible x values you can choose. So these are all the inputs. Or put another way, they're all the values of x that you are free to choose. Now that sounds strange. Why would I say you're free to choose them, but then make it sound like it's not totally free to choose? Well, for example, let me show you. Consider f of x as the square root of x. Now, we haven't studied this, but if we graph it, here's x, here's f of x. It's going to look something like this. For example, a point you'll find on here, if you input the number 4, what's the square root of 4? Well, you could put it in your calculator, you'll get 2. So an input of 4 and an output of 2. It's one of the points on this graph. To see all the x values on the graph that you may use as inputs, consider the shadow. And it's going to continue on in this direction. But the shadow that's cast by this function. that's going to tell you all the available inputs that you may use. Again, you can't take the square root of negative numbers. These are all the positive. So these are negative x, which we can't use. We can't take the square root of negative x values. But we may take the square root of positive x. So even though we're free to choose x, we're free to choose x within reason. We have to be able to actually use the x we've chosen. So the domain in this case we can choose everything from 0. And as long as the number's positive, it doesn't matter how big it is. As long as it's positive, we can choose it so we can head out towards infinity. So that's going to be our domain. Questions about that? Let me give you another one. Instead of a formula, let's say we just have a graph. Let's say we have something like this. Well, what x values are we permitted to use? Well, we can use x values from -3 to -1. Because you can think of this as casting shadow onto that x-axis. Or you can draw lines up to the function right here. But then once you get past -1, there's nothing to draw to. So we're stuck. But then we can pick up again. 1, we can go to here, then we stop at 3. So we can reach our curve, and we're done. So the domain here is -3 to -1. This is 1 to 3. Now we have to merge these together. So the way we merge them together, we'll write our domain as -3, -1, and glue to it the rest of the domain, 1 and 3. That's going to be our answer. Questions about that? Now let me move on to range. Range is all possible f of x values or outputs. It's all the possible outputs. So let's take something like this. And again, if I'm going too fast, let me know. I'm just watching the clock. Now for the range, we want to look at what's happening with the vertical axis, f of x. So we can start from the axis and we can reach our function. And down to 0. And it looks like this is just going to keep going up as our function moves up. So what we have, this is down here at f of x equals 0. Our range is going to be everything starting at f of x equals 0 on up. So the range will be 0 to positive infinity. Questions about that? We do one more example. Let's say we have something like this. Well, again, let's look across to our vertical axis. So it looks like we're going from 1 up to 2, but we got to be careful. This is an empty hole. So even though we have a point here, this is going to be a gap. This is going to be a hole. And then over here, even though we go from x is 1 to 2, we always have 3. So this over here we would describe as, this will go from, again, we're looking at the vertical axis now. We go from 1, but to not quite 2. And on this other side, well, it's just the 0.3 on the vertical axis. So putting this together, what we'll get for the vertical axis, we go 1 to 2, but not quite 2. And then we tack on that 0.3. And a point by itself gets curly braces. And that would be our range. The last thing I want to mention, I'm going to go a little long, give me 5 minutes, and then that'll be it. The vertical line test. So we've mentioned this idea called functions. And the idea of functions is we don't want duplicate inputs. So what we do, this is a way of identifying duplicate inputs on a graph. So what does this look like? Well, let's take an example. Let's take a look at something that's not a function, something that has duplicate inputs. So let's consider this set of inputs and outputs. And we're going to graph these on our Cartesian plane. So for 1 and 2, vertical line at 1, horizontal line at 2, they'll intersect right there. 1 and 3, vertical line at 1, horizontal line at 3, that would intersect right there. 2 and -2, vertical line at 2, horizontal line, the output -2, input and output intersect right there. 3 and 4, oh, need to go a little higher. I gotta change this, I apologize. Let's go 4 and 3. Change things up. Switch these, make this 4 and 3. Input is a vertical line at 4. Output, horizontal line at 3. Now this is not a function. The reason is we have duplicate inputs with the number 1. So that means if I say go back to my bags of silica, 1 bag of pure silica, am I going to get $2 for it? Or are they going to pay me $3 for it? I don't know. It's ambiguous. At 1 p.m., I'm at location 2, but also at 1 p.m., I'm at location 3. Can't be in 2 places at the same time. It's ambiguity. It doesn't work, at least for how we like to describe things in the cosmos. So how can we identify the situation on a graph? Well, if we put vertical lines through the points, we intersect our graph only once, at least at this point, and also at this point. So here, the vertical lines intersect the graph only once, or at 1 point. Even I go all the way up here. I drop down all the way down here. Go all the way up even farther. I'm only going to intersect the graph of these points at 1 location here, 1 location here. So far, that means I have a function. But if I intersect the graph at 2 or more points, that means I don't have a function. So if I intersect at 1 point with an infinitely long vertical line, I'm okay. But as soon as I intersect at 2 or more points, that means I've failed the vertical line test. And that means I don't have a function. Let me do one more example. And then that's it for today. I think I'm going overtime on my overtime. I apologize. Just want to make sure we cover this. So something like this. If we draw vertical lines through it, each vertical line intersects our graph only once. So this passes the vertical line test. The vertical lines intersect our graph only once. But this fails the vertical line test. Because the vertical lines intersect more than once. For this one, all vertical lines intersect once. So that's the vertical line test. And to fail the vertical line test, you only have to fail it once. Even if for all infinity, every vertical line you can come up with will only intersect the graph one time, but except at this one point, well, if it fails at one point, the whole function fails. So to pass the vertical line test, you have to be able to pass a vertical line through the graph of your function or the graph of your relation. And at every point where it intersects, there's only one point of intersection. If you fail just here, you failed. And that's it. Pretty hard standard. So that's it for 2.2. We didn't get to 2.3. We'll get to 2.3 certainly on Thursday. Just wanted to make sure we cover this. I know the definitions of functions and everything get a little confusing. 2.3 is going to be more sort of grounded out calculations. And again, I need to talk to you about the test. I might halt here, and we might instead do a review for the test. I'm thinking of doing that possibly on Thursday, so you have the weekend to study for the test, and then you could do the test over the weekend. And I might do a little bit of lecturing on Thursday just to make sure we have some good distance. But that's what we're doing. Any questions, let me know. I'm going to start office hours in about 6 minutes. So stick around if you have questions. Otherwise, I'll see you in office hours.